3B.
I'm videoing
Thank
for you. I'll video this for you. Okay.
Last name, A through K. Shame on him.
Okay. Yes, Nick is somewhat genius. We got this. Okay. Effusion. Bye. Come back and see us when you're done. Okay. Okay, you can tell me later. With your little sexy photosynthesis dance.
Or not.
You don't have to say yourself. I think you need a pencil. You guys did this last year.
I don't want to ask questions. Do you want to build a birdhouse? Like, no.
Do you want to build up?
Here. Okay. Okay, let's finish. We have to solve problems. Yeah? Let's do this. Effusion versus diffusion. Effusion means it's going through a small hole. Example, the balloon. We've all had the balloon that does not make it through the week. Yes?
Yes.
Why?
Because the particles go through the balloon.
Go through what part of the balloon?
The holes.
The core.
Where are the holes?
They're microscopic.
Okay, they could be microscopic, or I'm thinking about the one at the very bottom. Okay, the one that you blow in. That one hole that's on the balloon that everybody knows about, because that's how you blow it up. Okay, so that's commonly used as an example. However, most of the time it's a pinhole into a vacuum, because that's how they actually measure the rates of effusion. But we're just concerned about the fact that it says through a pinhole. Diffusion of a gas. If I had my imaginary perfume, okay, my perfume, I spray it on me. It's very highly concentrated here, very lowly concentrated back there by Grace and Grant. How long would it take for them to smell it?
2 seconds.
Yeah, probably just a couple seconds, because they're moving at like 300 meters per second. So it's not going to take that long to get there. However, here's my molecule of perfume. What's in its way? Tons of molecules. They're beating against each other, so they can't make a beeline for their noses. It's going to be hitting across all these other molecules that are in its way, because there's air here. And so that's why it doesn't technically travel that much of distance. It doesn't technically travel 300 meters per second in that distance, because there's stuff in its way barricading it and blocking it. So that's why it doesn't take, like picoseconds or nanoseconds to get to their noses. It actually literally takes seconds or minutes to get to their noses, because things are in the way. So technical definition, gradual mixing of a gas, but there's other gas molecules in the way. So that's generally why it doesn't effuse or diffuse at the rate at which we think it should with its individual molecular velocities. Graham's law, know it. I'm not going to go over it a ton. It's the inverse of A, rate of A, and then the molar mass of A is in the denominator in the square root one, and then the rate of B is correlating on the inverse direction. So essentially Graham's law is rate of effusion of a gas is equal to the square root of the inverse of its molar mass. But when we compare two gases, we actually literally have to write in both gas identities the rates of both gases. So the actual, like one you've probably seen in your book is probably rate of gas, or gas A, excuse me, is equal to the square root of its inverse of its molecular mass. But we write it like this so we can compare. Note to self, always, 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 if you know the identities of the gas, your math works out much easier if you put the lighter gas as the rate 1 or rate A. Okay, so I'll just put 1 and 2 there. That makes more sense. Because what happens is the lighter gas should be moving faster or slower? Faster. So the rate of the faster one over the slower one, the way you calculate the rate works out when you have the inverse related here. So this will be like technically the heavy one, which is B, over the lighter one, which is A. So this works out to like a whole number. Because I can say, gas A moves 2 times as fast as gas B, but it's really hard to relate and say gas B moves 1/2 as fast as gas A. So it's harder to say the fractional terms, so I like to always just recommend putting the lighter one on top. The way this works out, the reason why we can assume this is true is related back to the speed stuff we were talking about. So this right here is rate 1, rate 2, so the gases here are rate 1 and 2, or gases 1 and 2. This right here, I'm going to expand this out a little bit. Square root of 3RT over molar mass, 1. And this is square root 3RT over molar mass, 2. In this case, what is able to cancel? 3RT, top and bottom, yeah? But then you have a weird situation where you have square root of 1 over molar mass 1 over square root 1 molar mass 2. These are both, when you divide, don't you take top and the bottom and you pair them, and the middle two and you pair them? So then this would be rate 1 equal over rate 2 is equal to 1 times molar mass 2 and then 1 times molar mass 1. What does that exactly look like? Or almost? Graham's law. So what we can actually derive Graham's law from the root mean square velocity formulas. Okay, so we didn't make it up. It actually works out mathematically. And some of us are really math-minded, so sometimes I like to show you the proofs. Sometimes it's just for kicks and giggles. Okay? Okay, so here's some problems. At a given temperature, an unknown noble gas, we know the category at least, travels 1.26 times faster than oxygen gas. What is the noble gas? All right. So we know the noble gas is traveling faster or slower? Faster. So is it lighter or heavier? Lighter. So where should it be identified as, A or B? A. Okay, see how quick that was? You should be able to make those connections very quickly. Rate A over rate B. Well, we know A is going to be considered our, I'm just going to put NB for noble gas. B is going to be who? Oxygen gas. And please, please, please don't forget it's diatomic. Okay, so then equals our square root of whose molar mass goes on top? Oxygen. So what's that molar mass? 32 grams per mole. And then B, noble gas goes on the bottom, so we're just going to call it X. Don't know. So what's the first step to this? Solving this? Square both sides. Okay, so, oh, I'm sorry. Let me go ahead and write down the final, before I square. We already know the ratio. What's the rate ratio? 1.26. 1.26 is the times faster, so that's what this whole thing is equal to. Now I'm going to square both sides. Okay, so then 32 grams per mole over X is equal to 1.26 squared. I don't care what that is right now. Let's just show it. Then solving for X, you would do what? Multiply X on both sides and then no, not divide by 32, divide by, right, so X on both sides, cancel there, stays here, divide by 1.26 squared, divide by 1.26 squared, so 32 divided by, that's probably like close to 1.5, okay, so 32 divided by 1.5 in your head, think about it. What's 3 divided by 1.5? 2, so 30 divided by 1.5. 20, so is it like 21? 20, what is it? 1.6. See how close we were? Oops, that's not grams per mole. That's a, well, yeah, that is grams per mole. Okay, so X is 20-ish. So who will that be? Neon, yeah. So helium weighs, no, neon weighs 20, argon weighs almost 40. So you guys can look at your noble gases. Yay! You identified an unknown gas. Okay, compare the rate of diffusion of carbon dioxide and oxygen gas at the same temperature. Compare for me, Ansel. Who moves faster? So we got carbon dioxide and oxygen. Who moves faster? Or tell me your thought process. Right, why? Right, so this one weighs 32 grams per mole. Carbon dioxide weighs 44 grams per mole, simply due to its molecular mass. Lower mass increases velocity at the same temperature, because at the same temperature they have the same, no, average kinetic energy. They technically don't have exactly the same kinetic energy, because that would be hard to tell, so we know what the average is. Alright, so you can verbally explain some of these things. Oh, I had this demo set up yesterday. You guys didn't get to see it, but here's essentially what it looks like. And I do this in honors chem. Not all my classes get to do it. It just depends on how we are. I'm going to skip this. I'll come right back. This experiment right here. This is a common experiment you can see on the multiple choice part of the exam. They have a glass tube, and they take 2 saturated cotton swabs or cotton balls, and they stick it into the end. So we did this in class? Okay. Yes, it really, if you don't get the ends sealed all the way, the gases escape, and so you're like, I can't see the results. I'm like, neither can I. You did it wrong. Okay, but the cotton swabs are totally saturated, and they are stuck into the sides of the glass tube. They have to be stuck in there completely, if not, the gases will escape. The 2 gases are vaporizing from a liquid. So in this one we had hydrochloric acid, and then in this one we had ammonium hydroxide. Gosh, that was a bad mistake. Okay, ammonium hydroxide. But what does this decompose to? vapor. So those two things evaporate. So what they say is this is ammonia moving through, which smells awful, and then hydrochloric acid. Notice though, the gases move into a sporadic way. That sporadic way is something you probably learned in biology. It's called Brownian motion. Brownian motion. It's how diffusion works. It bounces off the molecules that are in its way. So it diffuses through, and then they meet. What happens when this meets is it forms ammonium chloride. And that ammonium chloride forms a slight solid, or like a whitish appearance. And so in the back, I'll show you guys, there's a little white ring in there. It usually doesn't develop for about 5 minutes during the lab. So it takes a very short time if it's done right. But why is ammonium traveling this far and the hydrochloric acid is only traveling this far when they started equal, this far apart?
I'm sure
Ammonium's lighter. So.
Okay, so I'm hearing combinations. It's faster because it's lighter. What's the molar mass of this one? 17-ish grams per mole. Molar mass of this one? 36.45 grams per mole. Okay, so you notice that one's almost double in size, so it's going to move less distance. What they could ask you to do is actually quantify it by looking at the distances between the two and identifying some unknown gas. Yes, ma'am. It just means moving in a sporadic pattern. You see this pattern? And it's moving in that sporadic pattern due to other molecules blocking its way. And I have the math worked out here for you. You guys have this on your paper already. You can see the root mean square is going to be related to the distances. So the distances, you can take the distances and determine the rate or the ratio in which they've moved. And so the ratio was 1.5. So like ammonia traveled a lot farther versus the hydrogen chloride gas. Hydrogen chloride gas is the best way to say that. And then you look at the ratio, plug in your values, and you can actually solve for an unknown. But you don't see that as often as you would want, but I do want to at least show you that there's a possibility. All right, do I want to do all these right now? I have to do a couple of them. You guys are doing those. It's not that intimidating. Wait. Okay, 8. An average, I have the answers, I'm going to double them off. Tell me how you would set these up. If the average kinetic energy per mole of hydrogen gas is 2.9 kilojoules per mole in a sealed container, what is the temperature of the system? Thoughts? First of all, what are our givens? So how would you write that? Uh-huh. Why would you be using that KE equation versus the other one?
Because that one you just need the R in temperature. You just need the R to get the temperature.
Right, because it's asking for temperature, right? So you have to use the one with the temperature in it. The other one doesn't have temperature in it, so that would be wrong to use. So that's why I have you write down your givens and your unknowns, because then you identify which formula is best for this question. That's why I've found the value in this. So hydrogen is our identity, and then we're looking for temperature. So then when you see temperature, you're like, oh, I know which equation to use. We're using the kinetic energy is equal to 3RT over molar mass in kilograms square root. So you guys try to solve that. Your math gurus. I got you. I'll pull it off in a second. This one?
That looks like the root square meter.
Oh, 3RT. I'm so stuck on the velocity right now. 3/2 RT.
Mm-hmm.
You don't have to know the identity technique for this one. Let's do this. Do this. This is review. It's awesome. Because the joules is what the values is. Yes. Tara made a really good point. Say it loud and proud. Because
Because in our value, it's joules, not joules.
yes, you have to have same units. I haven't taken attendance all day. Should I do that? I'll do that in a minute.
Just for now, we're working.
I know, but I'm videoing, so I don't want to send this video. It's weird when it's on YouTube. They honestly fix the help. My professor does. Some people are sick food like crazy. Any answers yet?
236.
Do we have any sig figs that we need to consider?
Possibly.
230.
230. Oh man, writing's still there. Okay. When you plugged in, or when you first of all, when you found your kilojoules into joules, you found the value that you're going to be having for your kinetic energy. I usually do something like this. I always solve for the variable of interest first. So I solve for T, and I'll plug anything in until I have my variable set up appropriately. And then I plug in the values that I know. The 2900 here is going to be your limiting factor of sig figs, and so you end up with 230 Kelvin. Yay? We're smart, Miss Enlow. We got you.
We're so smart.
I know. Thanks. Okay. Seriously, smartest people in the school. I kid you not. AP chemistry, smartest people in school. So true. Okay, find the molar mass of an unknown gas that has an average root mean square. So what is this little thing telling us?
It's the one that you roll.
So what variable is this? U erms. Everybody's last nouns because U erms. I don't know how to say it. Okay, so we got the root mean square, and we know it to be 167 meters per second, and we know the temperature. Which formula?
The one that you wrote earlier. The one that you wrote earlier.
Also known as, I can tell you. I'm just deleting this. Go for it. You are you gonna? We have a blue reference, or no, I think it's the white reference sheet. It's over there in the second box. I don't know if you're giving this on the exam. What's the formula? Yeah, molar mass in kilograms. All right, you guys plug and chug. Tell me the unknown gas.
She changes it depending on what it is.
No, it's not on here, so that's a memorization one. Sadly. I'm ready when you are if you want to shout her out. Do we have a number? Throw a number out there.
281 times 282.
0.282. What are the units though?
Did you convert to pounds?
Okay.
Okay.
Okay, so 0.282 kilograms per mole is what that denotes to because of this little joule thing being a Newton meter, and a Newton meter is a kilogram meters squared per second squared. Okay, so this is what we get for the molar mass. Convert to grams per mole. 282 grams per mole. And unknown gas. No, I just said from the molar mass, the unknown gas, not the IMD. It's like, I have no idea who that is. It could be so many things. Okay?
Yes.
Yes. Did you? It may be that you didn't put the parentheses and squared on the bottom in your calculator, because that's why parentheses are super duper important in your calculator. Tara's got this. Thanks, Tara. All right, I'm going to hold off on these. I'm gonna let you guys work individually. I'm not gonna work on this right now. That's what we had to finish from yesterday, but the whole evacuation drill and everything, that threw me for a loop. There is in your packet, there's a multiple choice. There's actually two multiple choices. But like for you practice, the one that you're going to start right now is called AP can practice. AP multiple choice. That dash gas is 1999. What says 1999 first? Who was born in 1999? No, it's not. I'll turn on. So you're going to start the one that says 1999. No calculator. Try it in your heads. Talk to a friend if you need some estimation skills. So take about 15 minutes. Get the multiple choice done. Do you see which one I'm talking about?
Yes.
Yes. It says 1999 on it. I mean, I'm sorry. That whole set. Sorry.
Okay.
It goes from 1999 to 1994. There's 20 questions there. I'll give you 20 minutes. 20 questions, 20 minutes. Deal.